Good day, everybody. This is Dr. Priyanka from the University of Queensland, and I'm happy to present the paper ID 1615. The paper is titled as SADE Secure Anomaly Detection for GPS Trajectory based on Homomorphic Encryption. The baseline idea here proposed in the paper is to come up with a secure method that can detect anomalous points in the GPS trajectories without compromising the user's location. So whenever the location is leaving the user's device, it is encrypted, and that has the advantage that it can eradicate or avoid most of the attacks that can happen or breach the data. The cloud service provider computes the anomalies based on some computation on this data and cleans the trajectories and sends it further to the third service providers. If you look at the architecture here, there are three main entities. First of all, the user, where the device generates the coordinates, that is the latitude, longitude, along with the timestamp, and a hash value is computed for each of these coordinates. Then it is encrypted using the standard failure homomorphic encryption and sent to the CSP. The communication channel between the user and the CSP is assumed to be insecure, and that's why the encrypted data is sent here. On the CSP, first of all, the received data is decrypted and the hash value is computed. If the hash value that is received and the hash value that is computed matches, that means that data integrity is maintained. After the validation phase, then different parameter values are computed, for instance, the distance, the velocity, and the acceleration. Distance is computed using the traditional Haversine method with some approximations. We'll discuss that in the next slide. After computing these three parameters, the anomaly points are detected and they're removed. Further, the cleaned GPS data is sent to the third-party service providers that can use this data for various applications. Now, if we compare both the methods, the traditional Haversine method and the modified Haversine method that is used in the proposed method, we can see that there are approximation to the trigonometric values. So based on the small angle approximation theorem, sine theta can be approximated to theta, and similarly, the product of the cos theta values can be approximated to 1. R is the standard radius of the Earth, and D is the distance here. We have experimented with the Microsoft GeoLife dataset that is considered to be a pretty standard dataset. If you look at the pictorial representation of these parameter values, we see that it is going almost along the same graph. So it's like the traditional Haversine method and the proposed SADE method is performing at par. If you want to look at the numerical values, this is the average numerical values for the computed distance, velocity, and the acceleration. And we have also compared it with the method proposed in the literature. So as a conclusion, we can say that SADE is performing at par with the existing method and securing the user's location. For instance, for the trajectory point listed out here, the proposed method gives the anomalous points at 8, 7, and 15, whereas the existing method in the literature gives it 9, 8, and 15. So we see that it is performing at par. As a future direction, the method can be made more secure and its robustness can be tested against various advanced attacks like the identification attacks, the signal jamming attack, or the spoofing attacks. These are our references. Thank you very much for your time.